Hello Panthers, part 2 of the VSEPR, valence shell electron pair repulsion model. I'm just quickly summarizing here in a table some of the example molecules that I used in the last video. And one thing you notice is we have double bonds and triple bond, or triple bonds, but I have double bonds like here, or single bonds like here, double bond, single bonds. But one thing you notice I have left out in any of these examples is I don't have any lone pairs on any of these molecules. And you know that sometimes when you write a Lewis structure out, you end up with a lone pair. So how do we deal with them? So first things first, simple, if you have a molecule that has no lone pairs on it, like these or any number of many other ones, you can just simply count up the number of bonding regions and you can figure out what the geometries are. And by the way, we call these the electron pair geometry. So that's what these names are right here, electron pair geometry. Now, if you don't have any lone pairs, the electron pair geometry and what we call the molecular geometry are the same thing. Let me say that again. If you do not have lone pairs, if you just have bonded electrons around each of the atoms, the electron pair geometry and the molecular geometry are the same thing. Later in chapter 10, it's going to be obvious why we distinguish between these two. Right now, it's not obvious, but let's just say we have two different types of geometries, a electron pair and a molecular geometry. If you do not have lone pairs, then you have the exact same thing. Here's the second point I want to make. For your purposes and for this class purposes, I only care about these three groups, 2 electron pair, 3 electron pair, and 4 electron pair as far as the molecular geometry is concerned. Okay, so I know there's potentially other molecular geometries with 5 and 6. You don't need to worry about them in my class. There might be a question on the final exam, but as far as organic chemistry is concerned, it's not a big deal. Okay, so a good question is, what happens when we have a lone pair? So let's start with a simple example of something like ammonia, NH3. Ammonia has 5 electrons from the nitrogen, 3 electrons from the hydrogen, so there should be 8 total electrons. So the Lewis structure looks something like this. Okay, so here's where we make the distinction between electron pair and molecular geometry. So we have 1, 2, 3 sets of bonded electrons, but we also have a set of lone pair electrons. Those each count as electron domains. So just like before when we were counting, we would say there are 4 electron groups around this central atom. So the electron pair geometry is called tetrahedral. All right, and the angles are approximately 109.5 degrees. We're going to clarify this in a second that they're not exactly 109.5 degrees. All right, but it's a tetrahedrally bonded thing, so a better way to draw this would be something like this. Nitrogen with a set of lone pairs up here, hydrogen, and then we have the same wedge and dash notation. Looks something like this. So now this one has a name that we call trigonal pyramidal. Okay? It's a triangle and forms a pyramid. That's why we call it trigonal pyramidal. Pyramid formed a triangle. What do we notice about this particular one? We notice we have 3 bonded electrons and we have 1 non-bonded electron. So we have a situation where we have 1 set of lone pairs and 3 bonded regions. Then we end up with this trigonal pyramidal geometry. All right, another example. H2O is another classic example of this. So my Lewis structure looks something like this. That's a totally legit Lewis structure. Unfortunately, it does not show us what the geometry of this molecule looks like. So once again, we count electron domains and we say we have 1, 2, 3, 4 domains. So this is going to be tetrahedral electron pair geometry. But the real drawing is going to look something like this. And you've probably noticed when I've written water on the board, I've always kind of written it in this geometry because this is what it really looks like. All right, and we call this a bent geometry. That's the molecular geometry. What does this consist of? 2 lone pairs, 2 bonded. If we have that situation, then we have a bent. Here we have 1 lone pair, 3 bonded, and then we have trigonal pyramidal. Okay, let's take a look at one with 3 domains. So SO2 is a good example of this. We have a sulfur, 2 oxygens, and there's 6 electrons each. We need 18 total. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, we check the octet rules. We see that the sulfur is violating the octet rule. So I'm going to erase one of these lone pairs, add in a double bond, check the octets. The octet looks good. There's actually a resonance structure for this. But you notice all the octets are good. Now remember, sulfur can violate the octet rule, but that should not be your first instinct. So now we're going to count domains. If you want to stop, count domains, see if you can figure out the geometry, that's fine. Otherwise, we'll keep going. 1, 2, 3 domains. 3 domains. Three domains. Means trigonal planar. And the real Lewis structure looks something like this. Sulfur, set of lone pairs, an oxygen, and an oxygen. And what do you notice? It looks quite a bit like the water, doesn't it? We also call this bent. So 1 lone pair, 2 bonded. We call that a bent molecular geometry. All right, so here's the table that helps us figure all these out. And if you notice what they have here is they have electron groups, and then they have it separated into bonding groups and lone pairs. All right, so you notice if we have 2 electron groups, we can only have 2 bonding groups. It's impossible to have any lone pairs, so we're going to end up with linear 180. If we have 3 electron groups, we got 2 different possibilities. One, like we looked at before, something like BF3. It's going to be trigonal planar. It's going to be 120 degrees. If we have 2 bonded groups and 1 lone pair, something like SO2 we just looked at, we're going to call that a bent geometry. And if we have 4 groups, we have 3 different possibilities. 4 bonds, 3 bonds, or 2 bonds, and then that would be 0 lone pairs, 1 lone pair, or 2 lone pairs. And we call this tetrahedral, trigonal pyramidal, and bent. And I've given you 3 different examples of that: water, ammonia, and something like CH4. Now, if you look down on the 5 and 6, there's more possibilities. I am not going to expect you to know seesaw, T-shaped, linear, square pyramidal, square planar, all these ones down here. I'm not going to expect you to know those. There could be a question on the final exam if you want to get one question right that you wouldn't have otherwise gotten right. You can memorize these, but these are not super important to me. These are important to me because organic molecules fall into one of these 3 categories. All right, so you definitely need to know those. Now, the one other thing you may have noticed is the angles. Did you notice this is 109.5, this is 120, this is 180, but it says less than 120, less than 109.5? What's going on there? So let's go to the next page. All right, so if you look at the next page, you'll notice here's the 109.5 geometry. if we had an ideal situation, this is NH4, or NH3 rather. So remember, it looks like this. The Lewis structure looks like this. So in my ideal structure, we'd have a lone pair set of electrons. We'd have another bonded hydrogen, and then we'd have one coming out of the plane and one going back into the plane. And we would say, all right, that's a tetrahedral. It's got 4. It should be 109.5 for all the angles. But it's not exactly true. It turns out that this lone pair is better able to repel these bonded electrons, and it forces these to have a smaller angle than the ideal case. All right, in other words, the lone pair repulsion is greater than the bonded repulsion. So it's like pushing down on these bonds and forcing them into a little bit lower angle. Turns out it's 107 degrees for ammonia. You don't need to memorize the number. You just need to know it's a little bit less than 109.5. And then likewise, if we say the same thing about a water molecule, now we've got two sets of lone pairs, and these are repelling against the hydrogens. And what do you think the effect's going to be on this bond angle then? It's actually going to be even smaller because it's got two sets of lone pairs. It's actually 104.5 degrees for a water molecule. All right, so here's the trend then. 109.5 with no lone pairs, 107 with one lone pair, and 104.5 with two lone pairs. Are those numbers exactly correct for every molecule? No, but the point I want you to recognize is that with no lone pairs is going to be greater than one lone pair, which is going to be greater than two lone pairs. You do not need to memorize the angles. You just need to recognize the trends. Okay, so that's going to conclude this video. So now we've talked about VSEPR. We've talked about complete bonded atoms around the central atom, as well as ones with lone pairs. Remember, you do not need to memorize all the different names for numbers 5 and 6, but you do need to know 2, 3, and 4. And the last video that we're going to make for this section is going to be on section 10.5, which deals with molecular shape and polarity. Now that we know how to write the molecules, we know how to write the shapes of them, now we can predict whether these molecules are going to be polar or not.